So I thought that was a marvelous piece of parody. I hope you agree with me that that was a very shameful day in our university's history, what we just saw, and that the idea that you have Alameda County Sheriff folks not able to at least dialogue with the students to get them to reach some peaceful, resolution to that, I think was what happened was, I hope, never happens again, folks. So we're talking about virtual memory. We're in lecture 2 of that. News of the day is optical computing has been one of the future technologies we've always seen, always a couple years away. The idea is you don't have the heat drain if you have current flowing on wires. If you have just light passing from A to B, you don't have the heat generated. And folks at Stanford have developed what they call the nanoscale single-mode LED, which can transmit data chip to chip 10 times faster than it can now with 1/1000th the energy. I thought that was pretty cool. See? Cool? Get it? Cool? Yeah. No love there. Okay. So we're right in the middle talking about virtual memory, hopefully trying to demystify it, another way to take it, another way to describe it that started with the real example of this eJournal. I spent a lot of time with the simulation with the eJournal metaphor. We're kind of going back to the standard set of slides now, seeing if that helps grab a hold of the slides that we had. So in general, looking at this memory hierarchy, and this was what we saw so far with the caches, and this is what we're doing with virtual memory. It's the same idea. It is providing the illusion of the size of disk at the speed of memory, just as the cache provided the illusion of the speed of cache at the size of memory. The unit of transfer here was blocks. From a cache to memory, unit of transfer of memory to disk is in pages. So you have some working set of pages that reside, that reside in memory. That was, you have an eJournal that can only hold 4 of those guys, even though you have 8 somewhere in the cloud or on disk or something else. I don't say the cloud meaning the internet, but it just means some other place. The OS can now allow multiple programs to run at once. There's no reason that you couldn't have your journal on the physical device as some other person's journal. They both could be somehow in physical pages, and somehow there's some, you think about the eJournal login, and I only see my pages, not yours. Pretty cool. You have protection among programs. So your virtual memory space is great. It's the idea that if you're living in a virtual space, whatever you do to your virtual bits, you can affect somebody else who might also be resident as well, because you're going to somehow corrupt or do something with your virtual space, and you can't touch my virtual space. That's pretty cool. So you could have programs can't touch the OS, another program can't touch another program, really, really clean protection. And each user of the eJournal thinks they have the whole thing to themselves. So that's all review. You've seen that, you've seen that, you've seen that. So we saw this already, the model that I have my memory on the side, and I divide up both physical memory and virtual memory into equal size pages. All the same. No worry about any what? Fragmentation. Right. In the malloc problem, here's a big malloc, then a small one, and then a big one. If you free the one in the middle, there's this little slice in the middle you're stuck with. You don't have that here. You never have that here. So, quiz question, final exam question, do you ever have fragmentation in virtual memory? Never external fragmentation. You might have internal fragmentation in which I've given you a full page, but you only used a byte of it. Right? What if your amount of memory malloc is roughly a page and a byte? Well, I'm going to have to give you 2 pages, even though you only use a page and a byte. So there is some internal fragmentation, but never external, in which you have these slivers. Okay? And so you have things map anywhere. Where do they map? In a way, you say, I don't care. In some sense, it's I don't care. Here is the key thing. This is exactly the picture you saw from the simulation. I have 8 virtual pages in my eJournal, and I use some translation map. That's a lookup table for each one of the 8 entries. So for every entry for every single virtual page, I need to know, where does it live? Does it live on disk or does it not? If it lives on disk, I need to know where it lives. If it doesn't live on disk, then the OS will handle that for me. And the OS will do the swapping so that by the time I finally get to memory, it'll be resident and be updated. So this address translation map or page table will tell me where my indexed by my virtual page number, which here is, look, 0 through 7. In binary, 0 through 7. It's the higher 3 bits of that 8-bit entry. The lower 5 was the offset into the page. In this particular example, the upper 3 was my virtual page number. That number from 0 to 7, I look up in that array, which has 8 entries, indexed to 0 through 7, and what comes out is the blue. In each of those entries, I only have to store 2 bits, which is what actually is the physical page number. I also need another bit to tell me whether it's valid or not. Is it actually resident or not? That's pretty simple. So the page, as we saw, is the unit of mapping. It's also the unit of transfer from disk to physical memory you saw in the previous slide. So my page table is literally no more complicated than an array. It's all it is. It's literally just an array indexed by VPN, the virtual page number. Here, 3 bits in that example. I look that up, and I get out a physical page number, which is now 2 bits. So it's a mapping of some number of bits virtual, which is 3 here, to a smaller number of bits, which is 2. Yes, Brennan?
Okay, so this sounds very much like a fully associative cache.
I love it. A fully associative cache. Except, interesting.
Except that you have this nice table which tells you where it is, so you can get things in constant time. Why don't we do that for fully associative caches?
So in fully associative caches, I never need to search. There's always a way that tells me exactly where it is. I never have to search. There's always a way to immediately get to it.
So using something like this table?
Yeah, I mean, imagine a cache having a lot of entries. The worst case is it here? No. Is it there? No. Is it there? There's got to be some table that keeps track of it. But in caches, it's harder, right? Because in caches, we haven't had a data structure to keep track of this page table, right? We don't have that. We also don't have the time it takes to keep a fully associative cache with an LRU mapping updated. What do you mean by that, Dan? Well, what makes a fully associative cache work? Hold that till the end, because I actually have a slide on fully associative caches. Just can you say that idea about fully? There's a question about this as being fully associative. It is fully associative. It goes anywhere. This is not direct map. This is not two-way associative. This is fully associative. And I'll get to that in a second. But the key thing I want to show here is this is just a simple lookup table into an array. And the physical page number is often called the page frame. And it's even called the page frame. Something's wrong with my simulator. Whoops. That was weird. I can't seem to quit that. Oh, no, don't get that one. That's the one I wanted to keep. Good. That's the guy I want. I want this. No, I want that. There. See? Page frame. I'm sure you hear. Zoom, zoom, zoom. Page 0 frame. Page 1 frame, right? So the point of that was it's called the page frame, the physical page number. Okay? Just to show you that one. All right. Bink. So here's how it looks. Here is how an array looks. I have my virtual address. And by the way, think of this in either the 8 bits wide in the eJournal, or if you're a little bit ready to jump into the real thing, 32 bits wide. So now explaining how the real system works. So this is a 32-bit wide number if we're talking about MIPS, or an 8-bit wide number if we're talking about this eJournal. Okay? I have an offset, which in the eJournal was 5 bits. In the normal MIPS idea would be however many bits it takes for the page table size, right? This offset is calculated based on what? How big is your page? It's the offset of the bytes into a page. So however big is your page? Page is a kibi. So how many bits would my offset be? 10. Okay? So this offset is uniquely determined by that page size. So here's a page table. The page number, the virtual page number, is the index. I'm saying the same thing over and over and over. This is just one idea that I'm just saying over and over in enough ways that maybe you'll get it. Inside the page table, you have an entry. That entry, the most important thing we've seen so far, is this physical page address, or the physical page number. That number gets concatenated with the offset. Offset just passes over, and I keep that 5 bits there, and now I have 2 bits out. And now I have a physical memory address. This page table is loaded in physical memory. We talked about that last time also. Okay? Here's some interesting things. One, we saw valid. Valid means are you resident or not? Are you in physical memory or not? We also saw this access rights. That protection means that we can actually determine whether a page, it's quite interesting, a page is read-only, whether there's a read bit, can you read or not? Can you write to this page or not? Can you execute that page or not? What might those things mean in MIPS world? What does read mean? Can you do an LW of an address that maps to that page? Exactly right. What might write mean? Can you do a store word or store byte or store double, all that, into that page? What might execute mean? Can the PC ever point to that range? Right? The PC pointing to a particular address says, that's what you're running. That's what you're executing. So that's a way to kind of have those 3 bits, read, write, and execute, actually say, wait, if I don't want to have anybody modify my code, then what might I do? How might I set my bits in some of the pages in memory? The memory that's associated with my code segment, what might I say to that? Yeah, read, execute only. Not write. All of a sudden, you can't change that range. The system is saying, as much as you try to change a PC and do a store word, you can't. I won't let you modify that page. Isn't that cool? So, the other cool thing here is page table base register. If I'm going to switch from your process here, this is the left side of the table, this left side of the group, to your process, 2 processes that live. Okay? If I have one page table and I want to swap, wouldn't it be really annoying this might be a lot of entries, by the way, a lot of entries. Let's start to talk numbers out here. Let's say I have 1 kibibyte page size. I have a 32-bit virtual address. How many entries in my page table? Let's count together. 1 kibibyte pages means how many bits for offset? 10. Therefore, how many virtual page numbers do I have? 22 bits, or 2 to the 22. How many is that? 4 MB entries. So now I want to switch from this process to this process. All right, here we go. Ready? Go. Start for a for loop and copy 4 MB entries from that thing to this thing. Pretty smart, right? Say no. Many things in life are solved by one level of indirection. Like, I don't know, having a uniform email address that never changes. And now none of us have to ever change our email address. If you give me that lifetime email address, perhaps from Berkeley's Alumni Association, and you decide to take 10 different jobs, I don't care. I send one mail to one place for the rest of my life. I never need to update my address book again. Who would like that system for their friends who are moving around? Me, right? It would be wonderful if you had a unique email address for you forever. Maybe attach to your social security number, but that's maybe too revealing. Just something to get to you before you have to graduate to college to get this alumni network valid thing. So, if you had a unique email address, you'd had that one level of indirection means that you can go ahead and take 10 different jobs and I don't have to worry about it. That's the power of a level of indirection. So watch this. A page table base register. I have one register, 32 bits. It points to your 4 MB table. If I want to change this process, by having one level of indirection of a pointer to that thing, all of a sudden, blink, erase those 32 bits, I write in 32 more bits, it now points to your table instantaneously, 1 nanosecond. You see how cool that is? How a level of indirection has saved you from copying 4 MB entries from this unique table to this. No, you each have your tables associated together. I just change one pointer, and the pointer now points to your table. Isn't that cool? So that's a really important piece of this slide. You're like, oh, blah, 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 address there. But no. You don't realize how important that register is. That level of indirection is telling you that you can now change tables, change processes with one store word. It's a register. It might even be a store word. Bam. I just change a local register as that's my hardware register. Bam, it's done instantaneously. One clock cycle. Pretty cool, right? You guys appreciating this? And give me some love. Give me some nods for how cool that is. Nods? The love? Yes, some nods. There we go. All right. So, in summary, a page table is an OS structure. The OS deals with all this stuff, right? I'm revealing the hood on some OS details that we've never really done before. Okay? There are several different ways to do this. Each process has its own page table. I talked about that. The state of a process is the program counter, the registers, and the page table. Before, we only talked about the first two, PC and registers. But now you know, there's a page table too that's associated with it. And that big 4 MB high and however many bits wide you have to deal with, which is a function of how much memory you actually have, that guy also carries along with each process. Make a new process, you got to make a copy of each of these guys. Because each process has its own copy of that thing. But to switch processes, I just change the pointer to the page table very fast. Okay? And this is what the bottom line says. Cool. So here's what's great about what VM buys us. Here's why we all use it. You can now share memory. You can have different processes all living together, sharing the same physical eJournal, physical memory, and nobody needs to know about their neighbors. It's this beautiful model. You also have separate address spaces. You don't have to worry about what's really built. You just have, I live in my separate address space that happens to be the maximum address space. And the best part about that is, as I take a program, written, compiled, developed on my machine, which has, let's say, 8 GB of RAM, and I move it to yours that has a KB of RAM, it still works as long as the KB is more than a page size. You know. The point is, I don't have to recompile. It just works. It just works. It's really beautiful. More of my pages are going to live in memory than yours because I have more memory than you. My program is going to be faster because I'm not doing disk swapping as you will if you have far less memory, but it still works. Code that was written for the same architecture, for the same instruction set architecture, on a machine that had no memory at all, can work in my really wonderful one just faster because more pages will be resident. Awesome. You also don't have to be given every page at the beginning. I kind of mentioned that it was a page on a need-to-give basis. So when malloc is growing, when the stack is growing, when you're starting creeping up in more memory, you basically only use the pages you've ever have visited. Isn't that cool? So if you just write a hello world, how many pages? There's like a page down on the code side and a page up probably at the top for the stack, and you're done. If you don't have to make any mallocs, there's no heap stuff, there's no static, 2 pages, you're probably done. That's awesome. There were 4 MB pages. If you had 1 KB page size, you have 4 MB pages total in the virtual address space. How many do you have in the real? Well, let's say you only have a gig of RAM. That's not much. Okay? So that's a fourth of that. That's a fourth of how many virtual guys you had. So it was 4 MB pages. Now you have 1 MB pages resident. Of those 1 million pages, roughly, only 2 of them are used for a hello world. You thought you had access to all 2 to the 32 address space, but because you didn't make any big mallocs, you don't need them all. You just need 2. 1 for the code segment at the bottom, 1 for your stack up top. You need 2 out of 1 million. Done. I can now be running how many copies of, I can now be running hundreds of thousands of hello worlds all at once. Every one of them lives resident. But because they don't use the whole thing, it just works. Isn't that awesome? So you only get memory on a need-to-use basis. When you ask for it, malloc, or when your stack grows, and you kind of creep past a next page, I give you one. Malloc guy will give you one. So malloc will give you at that. And that's also why malloc will fail. That's exactly, malloc says, hey malloc, I want this big chunk. Malloc says, what do I got? He says, how can I get the memory? He says, nope, you can't get it. And malloc's going to fail, possibly because you are exceeding the number of pages that were available to you. Not physical pages, but virtual pages available to you. Okay? Question here.
If you have so many processes running, then you theoretically have so many page tables that you fill up your RAM.
That's a good point. Page tables take a lot. That's exactly right. Page tables is a big overhead. That's exactly right. And the smaller, where's my thing? The smaller my offset, the smaller the page size, the more the VPN is, and the higher my page table is, right? So you kind of want a nice sweet spot of what the offset is. You know, you end up having, there's pluses and minuses of having a page table, the page size grow and shrink. What's the advantage of having a bigger page size? Bigger page size, so bigger bits for the offset, smaller, right, fewer pages, and now, why is that a good thing? Why would that be a good thing, fewer pages? Smaller page table, so that's an easy one, okay? But what's, now think of some code. You might have a lot of internal fragmentation. You might have these big pages, but you're only using a byte or 2 here, and you got this huge thing I've given you, right? It also means when you go to disk, you have to grab more stuff. Bigger pages means more chunks to get if you make 1 page, I make 1 memory access into some random place, I have to get this great chunk here. What's the worst code you could ever run? Give me the worst code from memory point of view you could ever run, ever. A big malloc, then how do you access it? Do you kind of go linearly? Do you kind of jump by stride? What's the worst thing you could ever do? Jump by how much? A page size. The worst thing you could do, and try this please, is have a little for loop that says for I equals 1 to number of pages, memory, access memory of I times the page size. Every single store word or load word is another page. If you have big pages, it's like, oh, grab a big handful, that's yours. Grab a big handful, that's yours. If you have smaller page size, not so bad. But if you have a big size, that kind of code is going crazy. That code is going crazy anyway. Whether you have big or small thing, it's doing the worst thing you could ever do. Try that. It's really fascinating. That's the worst thing you can do. People say, no, just do a for loop sweep through. No, you need to sweep through. Just hit it by page size. That'll do the worst thing. Because every page size is going to bring another page from disk. And you'll have fault every single one. So here's your page table entry. There's your valid. There's the access rights. I mentioned here read only, read, write, execute. I mentioned that. Here is a picture of two different processes. Two different users even. Forget different processes of the same user. Two different users on the same system. They both divide them up. They have their local page table. And they just seamlessly are sharing physical memory. It's beautiful. It's a beautiful thing. So A is using some but not all of it. And B is using some but not all of it. And it's just beautiful. There's no external fragmentation. You've wholly filled it up. And if B starts to grow, what does this system do? It's got to buy B more pages, but they're all filled. What does it do then? What do you think it does? It's got to swap, right? It's got to take some of the least recently used pages, and if B has been active, then probably all of B's pages are the most recently used, and kick some of A out. So A thought it was resident, and kind of the CPU gave its attention to B, and A was like, okay, I'm cool, I'm resident, I'm going to be fine. And when A comes back, A's been kicked out because B was a memory hog. Can you think of a program that's a memory hog? Photoshop. What else? By the way, Photoshop has preferences that lets you actually set up its own local disk. I think Photoshop years before, Photoshop was cool because Photoshop, years before you ran on systems that all had VM, had its own disk, a little scratch disk that Photoshop would use itself. Photoshop is the unique program that lets you have almost a transparent interface to malloc. How do you have that? New document. How many pixels wide by high? You multiply that out, and that is literally a call to malloc. Isn't that cool? So you go to Photoshop, you say, oh, I want to just malloc some massive thing. Ready, watch. 1,000,000 by 1,000,000. Your disk starts spinning, this big canvas opens, because you have told Photoshop, I want a massive virtual, it's a virtual address space, I want a big malloc of all those pixels to be able to handle as I draw in 1,000,000 by 1,000,000 canvas, and you are literally, basically transparently sending a massive malloc call. Very other programs let you do that. Very, very few other programs let you kind of do that. The PowerPoint, no. Word, no. But Photoshop, X by Y canvas is a call to malloc, basically. It's pretty cool. So, let's compare caches in VM. In a cache, the unit of transfer is a line or a block, and in virtual memory, it's a page. In cache, when it's not there, a cache miss. And we talked about 3 kinds of cache misses, the 3 C's, which are compulsory, conflict, capacity. Okay, we have the same problem with page faults. We have compulsory page faults, the ones that you have to have. You have capacity, which means the amount of physical RAM isn't big enough, and the way you solve that is you get more RAM. You go to Best Buy, you go to Fry's, you get more RAM, that you'll solve your capacity. How about conflict? Well, I'll get to it here in a second. Watch this. Fully associative. You never have conflict misses if you have fully associative style of caching. Because conflict means that 2 guys, like in direct mapped, from 2 different places map to the same place. Even though there may be room in your cache, these 2 guys happen to map to the same place. That's never the case in fully associative. They go anywhere. So you never have conflict misses with fully associative, and that's good. That means I've reduced, of the 3 things I could try to reduce, all the kinds of misses I had, all the kinds of page faults I had. Can I reduce my compulsory? Basically, I can't. Can I reduce my capacity? Sure, buy more RAM. Can I reduce my conflict? I've done it. Fully associative. So I've done as best as I can to not have to go where? To disk. Where's disk? Jupyter. Right? It really matters I don't go to Jupyter. So I'm going to have all the data structures I can to make sure I don't go to Jupyter. What does that mean? Now we're back to Rowan's question. Fully associative, okay? What do you have to have a, oh, I should try this one, next one. Brink, that's the key thing. LRU. It's LRU with fully associative. What does that take advantage of? Temporal locality. It totally is exploiting that, right? So how do you do LRU right? I've got 4 million pages. What does LRU mean? It means I have a what? A sorted order to those 4 million pages. Does that make sense? LRU means it's, oh, I'm full, I need a page. Who do I kick out first? I go to the end of my line, I say, sorry, you are the 4 millionth page to be accessed. You're the oldest one. There's cobwebs, there's spiders rolling, and I say, sorry, kick him out. I first check if it's what? Dirty. If it's dirty, what do? I got to write him. Oh, man, go to Jupyter and write it, and then read the guy I want. If it's not dirty, what can I do? Just read the guy in and just clobber him, overwrite it, because it's not, they're consistent, okay? So LRU is critical. So think about this. How do you do LRU with a fully associative cache? The point of a cache is you're supposed to be able to respond to a memory access at the speed of a register. One clock cycle, 2 clock cycles. How fast can you update a perfectly sorted list with how many total lines were in normal caches? I don't know. Hundreds, maybe 1,000, depending on what your cache size is. Are you going to keep a fully sorted data structure and update the sorting of that in 2 clock cycles? Can't be done. But if I'm talking about using, I don't know, you guys know that there are 3 tiers of speed. There's nanosecond level access, which is register speed, right? A gigahertz clock is nanosecond level access. There's microsecond level access, which is roughly 1,000 times slower than that, maybe 100 times slower than that, is memory. Then there's millisecond access, which is disk, right? There are 3,000 time difference. That's a massive difference. That's not the order of magnitude. That's 3 orders of magnitude base 10 or 10 base 2. 10 orders of magnitude base 2 in between those 3 tiers of registers to memory, roughly, right, to disk. So if you want to be able to have a data structure to keep a full track of who's, okay, so it's A, B, and C. Nope, are you touching C? Well, C has to move over here and shift that down and do that. Do I have time to do that at the level of nanoseconds? No way. At milliseconds, so I can save myself at microseconds, so I can save myself a millisecond access? I certainly do. So I have time to be able to keep track of all the LRU so I don't have to ever go to disk if I can ever help it, thanks to conflict misses, which is why we do fully associative and why we do LRU, because I have time to do it. And that's why we don't have time to do it at the level of caches. Okay, so we do 1 bit, right? You saw the 1 bit, when you access it, changes the bit, and that's the search level you kind of do, but that's all we do. 1, maybe 2 bits tops, but you don't do anything else because it's much harder than that. And hardware to do it. Yes? No. To find what?
Find the page where the page is.
Page table told us.
Yeah, but through the page table, because it could be. Oh, wait.
No, I know where it is. You say virtual address, page table, physical address. Bam, instantaneous. There's no linear search. And because you've touched a page, I now have to take this out and move it to the top, because you just accessed the page. If it wasn't the top, I make it to the top, and now these guys go blink. And whatever data structure you use to kind of keep that perfect ordering, think about how you want to keep something sorted. You could use a heap. You can use whatever data structure you want at the OS level to keep things fully ordered. That's the idea. Okay, yes, Claire.
When you use it, and then it becomes the most recent one, do you change the address in the page table as well?
You don't change the address unless it moves. Unless you brought it from disk and brought it in, you don't need to change it. The page table is only where it lives in physical memory. There's another, I haven't shown you any picture, there's another kind of ranked ordering of who's the top guy, who's the next guy. It's like, who's the top student in the midterm to last? If all of a sudden you get some regrade, you bump to the top and you just adjust it. That's some other file that's not the page table that keeps track of the ordering. That's a good point, just to make sure we're clear on that. Yes, question back.
Yeah.
You
also need to go to the other process
Exactly. You better make sure the data structures are consistent. If you're kicking out, if B is doing a lot of access and it's kicking out somebody from A, you got to go back to A. It's the OS's job, not your job, to take A, make sure that the guy kicked out, that's now kicked out, blah, 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 write it back, all the things you do. You know, A says, is it dirty? If it's not, the same thing we just checked it for your own, but you do it for A. And you need to update that table. Certainly update it for the valid bit. It's no longer there. Exactly right. It could be as easy as, literally, it could be, if it's not dirty, it could be as easy as saying invalid. 1 bit, and you're done, right? So you don't have to go to Jupyter anymore. Just update the guy in memory, and you're done. But it's dirty, you got to go to Jupyter and write it out. Okay. Why do we only do write back here? Why don't we do write through? I mean, this is like both, right? Write through or write back. Why couldn't we consider write through? It's like, if those who kind of get it, it's like, that's ridiculous to have a write through. Write through says every memory access, you keep your page in memory consistent with disk. So let's write to memory, and let's also go to Jupyter, every single memory access. That's what write through would mean. Yeah. But you'd save yourself a dirty bit. Yeah, that'd be funny. Okay. So remember, because of this beautiful idea of having them all the same size, the external fragmentation is solved. Love it. That's like my toothpaste example, right? They're all just packed nicely. The OS has to reserve some swap space to be able to, for each process, and I'll actually show you that on Friday, some really cool stuff. I'll reveal the Mac's internals, and I'll show you how that kind of stuff looks like on the Mac. To grow a process. So what does to grow mean? When would you grow it? 2 cases. When does a process grow? Malloc and stack. Or it just could be a call. It could be a lot of calls. Somehow the stack is grown and added more space. It doesn't have to be recursion. It just can be A calls B calls C calls D. You end up eventually needing that. So 2 ways, right? 2 ways that grow. 2 arrows that grow. The stack could grow, the heap could grow. So if there are unused pages, if there are some spare physical pages that aren't being used, grab it. Bam, I got it. I don't have to do anything. No need to upload anybody. Okay? If not, well, I've got to swap some old guys to disk, and they may not require disk write if they're not dirty. And LRU picks the guy there. I said this before, and I said that already. So here's the stack and the heap growing. I show you here that stack is the guy that grows, and heap is the guy that grows. You remember, static and code don't grow, so you don't need to worry about that at all. And so a very small hello world is going to have a page down here for the code. Probably is not writable, those pages. And you have probably a page up here for the stack would be read write, but not execute up there, right? You wouldn't be able to set PC up there. That make sense? And as we know before, for now, OS somehow prevents the access between the heap and the stack, and let the OS handle that. Don't worry about that. So here's a problem. And this came up in office hours today. Okay, so I do a map of every access. Well, that means this indirection via the page table. So I give it the virtual address. I need the physical address. How do I look it up? I look it up from this page table. Where's page table? In memory. So before I even went with a store word and load word, to even know what $S0 32 bits was in real memory required a lookup into memory. So now I've got 2 memory accesses. For every memory access, it becomes 2. I've now doubled it. Oh, Dan, but thinking, virtual memory is so good for all these 20 reasons, you don't matter about the one guy. Well, it's still annoying. Every single memory access, I've now slowed my system. Our memory-heavy process is now slowed down by half. That's crazy. I don't want that. So, look at this. Since small is fast, and we know that caches are a good thing, why not have an explicit cache for just the page table entries? The most recent page table entries that you've asked for, I keep in a cache. Silence in the room. And for historical reasons, I actually don't know the etymology of this. Do you know where this came from initially? I never did know. Yeah, why is it not called a page table cache? I would call it, if you were me, a page table cache. Yeah, the translation, it is the translation, and it's kind of a look-aside buffer, but you put the cache in there at least, so you tell me it's a cache. Anyway, they call it a TLB, translation look-aside buffer. So, now this is the picture. This is like, oh, I love this day, this moment right here, because this is the moment that all along you thought you were in, 32-bit space and that was it. I told you now in the last 2 days you weren't. You were actually working in the virtual space, and the physical space is different. But there's one key difference on this whole slide that you have never realized. Here's the algorithm. Processor says, hey, I need a load word or store word. I'm going to be accessing memory at some point. Okay? So, or I even look up what the address is. We could be talking about the instruction level memory access rather than just the data level memory access as well. The virtual address comes out of there. You're thinking in 32 bits. All the thing you built is a 32-bit wide MIPS processor. So 32 bits comes out of that to the memory system and says, I need 32 bits. The first thing you do is look it up in the cache. Have you asked for those bits recently? If the TLB, which is a local copy of a couple of the things, it might not be 4 memory entries. It might be, 128. It might be a small little guy. If it's there, I've got it. If it's there, then I have a TLB hit, and out comes the physical address, which is really the physical page number. You concatenate the offset, and you got your physical address. If it's a miss, then I do my standard thing, and I go to my page table. I look it up in the I go to my virtual page number. I find the index. I get now the physical page number comes out, and I get that. I concatenate it with my offset, and I'm done. Then I go into the cache and do the rest of the cache to memory stuff. But watch this. Class, what was T plus I plus O up until 10 seconds ago? 32 bits. When you went to cache based on a virtual address, which you thought was the same as a physical address. It's different. You're going in with a physical address. That is different. So from now on, when we say, oh, here's a direct map cache, like weeks ago, it's a direct map cache, here's the parameters of it, and you say, okay, there's a T and an I and an O. What do they add to? They don't add to 32 anymore. What do they add to? They add to however many bits is your physical memory. If I have a gig of RAM, that's 30 bits. If I have a meg of RAM, that's 20 bits. That's what T plus I plus O gets to. And what does that really affect? Does it affect O? No. What's O affected by? This is like experts now. Block size on your cache. The O is block size. What's I? Number of rows, right? Number of blocks. So that doesn't affect by this. What's affected by this new discovery? T. The tag is now different numbers. Because the tag used to be, it's like 32 minus the I bits minus the O bits. Now it's however many bits I really have minus the I minus the O. So this, for those of you still blurry on caches and blurry on VM, just blew you away. It doesn't, I don't know, it's all fuzzy anyway. But for those of you still hopefully with me and just following slowly with me, that's a cool realization. That all along you thought you were caching virtual addresses, and I'm telling you, you weren't. You were caching physical addresses because it happens after the lookup. Because it happens after the lookup, you are caching now fewer bits. Yes?
Two questions, actually. How many TLBs are there, and are they direct maps or some kind of...
Does it say the next slide? There, right? There. Second bullet is your second question. And there's one TLB. It's a physical bit of SRAM that's on your system that's faster than main memory RAM, and it's a normal cache. It's just a cache reserved for the page table entries.
So then do you have extra bits to tell you which processor the virtual memory is? How do you differentiate between, say, address 0?
That's a great point. The moment you swap processes, you got to flush the TLB. The TLB is only for the active page table, right? Because it's about the page table mappings. If you all of a sudden switch processes, you got to throw out everybody that you've done recently, because otherwise you say, oh yeah, it's there, but it's really not anymore because it's a different page table. It's the mapping. In that picture where I had the two little page tables for A and B, it's like the small cache of the A or the small cache of the B. You can't just swap the page index, the page table base register. So now a different process takes over, but keep the TLB because the TLB was about A versus B. No, TLB is not A and B combined. TLB is per page table because it's about optimizing that little lookup table of which there's 2 copies or n copies, 1 for each process. Okay, so here's an analogy that may happen. I think my analogy is better than this. This is the original analogy that was given to you, and compare this to the Great E-Journal. The book title's like the virtual address. It's a title out in the cloud that's big. The actual Library of Congress call number is the physical address, and the card catalog. You guys remember who has a card catalog ever they've touched in the olden days? Nobody. Okay, maybe some people went to high school still have. I used to go through and find the call number, which was exactly where it is exactly where it is from the virtual address, the book title, to the call number. Right? Oh, I want Huck Finn. Huck Finn is this virtual address. I need to look up what number it is. That's the lookup table, which is like the card catalog. And now, here's the cool thing. There's a valid bit whether it's in this library or not. Isn't that kind of cool with the library? It is. Okay. And then I might even have, videos have a one-day rental, books have a week rental. That's like the access rights. So in some sense, there is a model that connects with your library metaphor. Okay, clickers, and on time. Look at this. Powering on for the clickers. Awesome, team. Feeling good. True and false. Locality is important, yet different for cache and virtual memory. Temporal for caches, but spatial for virtual. And the second is virtual memory helps both with security and cost. Yes?
I didn't necessarily want to ask it on.
Okay. Let me mute while I'm waiting. Go. Oh, boy. So it started out all pointing toward the right answer, and over time, the wrong answers have filled in the gaps, like spackle. I like that. So that means we're going to stop and discuss. Go. Back and action. And let's see if you guys can. There we go. It's now centered on the big one here. And now let's see. Keep going. I love it. Smoothing out. Very good. Keep bringing it up. Keep bringing it. Well done, team. Boy, look at this. Your neighbors have set you straight. I love it. Okay, ready? And freeze. Look at the difference. Ready? Here's 2, there's 1. There was all this stuff over here, and watch how it just kind of floats away to that one. Whoops. Floats away to the right answer, which is in fact B. So let's do that one, and let's do this, and let me show you why. So why is that? Well, my goodness, both of them have issues of spatial and temporal locality. Caching it all is the temporal locality. And the size, the fact that there's not just one byte or one word, but large block size and large page size, is the spatial locality. So it's certainly helpful for both. So that's false. And yes, we need security and cost. The fact is security protects your process from another process, and cost means that you can actually spend half as much money on memory and still get your program to run. It just will run slower if you're doing more page swapping. But good stuff. That's true. So there's your B. Bink. So in conclusion, we're doing great, folks. We're doing great. And by the way, the slides here are all the same as slides on Monday. I just wanted to spend more time on the thing. We're going to spend more time looking at the TLB and details of that. As you'll see in lab as well. You'll see that same camera simulation there. So the only thing that's new really here is that the TLB is a cache of those guys. That's the big new thing you learned today. And that spatial locality is critical. That's the page size. Is the spatial locality benefiting from that? The other piece is that as long as you have enough memory to handle your working set of pages, you're not going to notice. As long as you have your stack, the part of your heap that you care about, and your code loaded resident, you can have 3 or 4 pages and think like, I own the whole thing. I own the world. Only 4 pages you're touching and 4 pages are resident, and you're just as fast as if all of them were loaded. That's awesome stuff, thanks to VM. All right, we'll see you on Friday.